And now we're going to look at projectile motion. So for projectile motion, we can do the horizontal distance by taking t, which is the time, times the initial speed times cosine. So basically, what you're going to do is if you want to know the x equation, it's anything that deals with horizontals. So the time of objects in flight will affect the horizontal. The longer it's in flight, the longer it'll travel. So that would be included. Its initial velocity would matter, and its angle would matter. Since we're talking about x, you treat it with cosine. Now, as far as the y on a projectile motion, think about what comes into play. First, you do have the same equation as above, but with sign for the y. So the time it's in flight times its initial velocity, and then you would use sign. But you also need to subtract here half of g times t squared. What does this g stand for? It's gravity. So gravity, there's two values for. Gravity, we can use 32 feet per second squared is how we think of that. That's why it's time squared. It's 32 feet per time squared. And then there's also, if we're in meters, 9.8 meters squared. Okay, and we'll multiply that times a half, and then plus the initial height. These are anything that might come into play in the y, so it might be shot not from the ground, but a little bit up. So these formulas are also on this form. They're right above conic section. You'll see them right here, where here, this S of t, if you look at the equation, you'll notice is very similar to the y equation. You have gravity, you have the initial. What they don't include here is the sine theta, and then the initial height. And then this one, oh, I'm sorry, that's because it's just free fall. That's not being shot, it's just something falling. Here it is, vertical position. This is the formula they just gave you right here, and here's the horizontal formula. So those are on our formula chart. So it says here, this problem, example 6 for projectile motion. Shane Leckler of the Oakland Raiders has a record career punting average with an average of 46.47 yards. Suppose that he kicked the ball at an initial height of 2 feet, an initial velocity of 26 yards per second, and an angle of 72 degrees. How far will the ball travel horizontally? So here's what that means. He kicks the ball. So here he is. And you all know I'm not the best artist, so I'll put his leg up because he's kicking a ball. And what's going to happen is this ball goes up, and then it comes down. All right, now that's obviously not to scale, but this is the idea of what's happening. Now he kicks the ball at a height of 2 feet. So this right here is 2 feet. And honestly, this ball would come on a little bit further till it hits the ground. Now he kicks it at an angle of 72 degrees. So that means if we wanted to put on here the angle the ball comes out, if you went from the x-axis up here this way, it would be 72 degrees. Whoops, dyslexic there. Let's try that again. 72 degrees. And he's kicking it at a speed initially of 26 yards per second. That means as it comes off like a vector, and I'll do this color in red. It would come off as a vector like this at 26 yards per second. So I'll do 26 yards per second. That's how it comes off. So how far will the ball travel horizontally? What we want to know is, what is that distance? That's what we want to know. So here's how we solve this. You could write it as a parametric equation, as an x equals equation and a y equals. And going back to the formula chart, x is always initial velocity times cosine times time. So it's the initial velocity, which is 26 yards per second, and then times, and we need to be careful in units, so just keep track of this is yards. 26 yards per second, and it's doing it times cosine of the angle, which is 72 degrees, and then times time. That's what the formula says right here. Now the y equation would be like this. So we'd have negative 1/2 g, which here, this is where I was saying we need to be careful, because g is in feet at 32 feet per second squared. So honestly, what we probably need to do is go back here and either divide this by 3 to get it to yards. So that'll probably be the easiest way since we're at this stage. So g is going to equal, that's just 10 2/3. 10 2/3, or we can just leave it as 32 over 3 yards. That's what we just changed there, per second squared. So I want to put negative 1/2 of 32 2 over 3. That's yards per second. That's the g. Let's go back to the formula. G times t squared. And t we're just going to leave as t squared, like that, plus, it's basically the same formula here, but the only thing that's changed is we changed it to a sine of 72 degrees times time. And then at the end is, if you go back here, it's the initial height. What was our initial height? It was 2 feet. Whoops. Sorry about that. Let's go 2 feet. So now we go to our calculator, and we're going to graph this to find the distance. So I come over here, and I'm going to clear this. So I go menu, I'm going to go graph entry, I'm going to choose parametrics. And now my equation was parentheses 26 of cosine theta. Now instead of theta though, they're going to use a t. No, I'm sorry, we will put a theta there. No, it was 72 degrees. Sooner or later I'll get it right. It was 72 degrees, and then there's a t on the outside. Sorry, my calculator's messing up on me. Here we go. The t right there. The calculator added an extra parenthesis around the 72 degrees. Now here, for the y equation, it was negative 1/2. I don't know why it keeps messing me up, but
What is the direction?
1/2. And then our g, we said, was 32 over 3. So another fraction, 32 over 3, because there's 3 feet, 1 yard. And then we had t squared. Then we had plus. It's basically the same equation as above, 26, but this time we're going to choose sine. And it was 72 degrees. And make sure you hit the degree symbol just in case your calculator's in a different mode. And then you put the t on the outside right here. And then we do the plus the initial height, which is 2. And this will probably be kicked way too long, but we'll just check the work anyways. Press enter. Here's the fly of the ball. I'm going to go menu, window zoom, and I'm just going to hit fit. This will usually zoom it way out, and you can see this is the fly of the punt. He punts it way up in the air, and it's going to hit the ground right here. We can trace this. Menu, trace, and I can see as I'm watching, this will tell me how long the ball is in the air. My calculator is way off right now. But at 4.7 seconds, we can see it's about to hit the ground, and it's traveled 37.8 yards. If I wanted to, I can zoom in. So I'm going to go menu, window, zoom in. And I can zoom in here really close, and I can see exactly how far it traveled. And this time when I go menu, trace, graph trace, this time, why is my calculator messing up on me? I don't know what just happened. It just zoomed way off. Let me fix it. Okay, I found it again. And so now what I'm going to do is I'm going to trace this. So I'm going to go menu, trace. How? Okay, and now as I trace it, now see, here's what happens. As I zoomed in, if you go back and forth in time, you'll see that it just jumps past. The way to fix this is to use that T step I was showing you earlier. That if I use T step, I can change it to where it will not count by time quite so fast. So I'm going to go tab, and I'm going to go to my equation, and instead of saying count by, see how right now it's counting by every 10th of a second, I'm going to change it to like every 100th of a second. So now, as I trace this, menu, trace, graph trace, it's going to go a lot slower. Well, I say that, it's still going too fast. So I go menu, and change it again, tab, and I'm going to change this one, this time, to 1,000, and I'll graph it. And so now as I trace this, let's see what happens with this. It's still going way too fast. I'm sorry, I was going the wrong thing. So when we go to trace, where you change it is trace step, not on the T step, you're doing trace step. And so here, we're going to enter value, and we're going to want to count by, let's make it by like 100. So now when I do hit trace step, and I trace it, now it should go a lot slower. So we'll graph trace, and now as you can see it goes a lot slower. So we're getting closer. We still can tell it's between 37.8 and 37.9 yards. And if you want to know exactly which one's the answer, I'm looking down here. Again, you can go to Menu, Trace, and you go to Trace Step. And you change it now to 1,000. Now as we trace in here, we can see that it hits the ground at 37.9 yards. And how I know it's there is because I have a y value that's positive and now one that's negative, and the x stays the same. So it'd be 37.9 yards. That's how far the ball travels. So that would be our answer here. How far does it travel horizontally? 37.9 yards. And now if you needed to know like the maximum or anything like that, you can go back and use the trace as well. So you have one to try here and see what you can come up with.